All right, so in the last lesson, we managed to get our 3D dice to get rendered and displayed in augmented reality. Now, the only problem is that it looks a bit weird because it's kind of just free floating in midair, which is not very realistic for a solid object. So in this lesson, we're going to focus on plane detection. So we're going to be using a structure within ARKit that allows us to detect horizontal planes in the camera image that's captured. So at the moment, we can only detect horizontal planes because, as you can see, the options only include horizontal. Now, we think that in the near future, vertical plane detection is going to be added in here as an option, and I expect that the Apple engineers are probably just working on it as we speak. And that was certainly the indication that we got at WWDC. So talking to some of the engineers, they did seem to hint that this was something that was going to be enabled within, a short period of time and not something that we would have to wait for, say, iOS 12 to appear. So that's really encouraging, but it does mean that in the meantime, we won't be able to do any vertical plane detection. So all of you guys who have ideas of, hanging paintings onto the wall and seeing how it looks in AR, you're going to have to hold your horses for now until they update the plane detection options to include vertical. But horizontal is good enough for our dice app because what we want to do is we want to be able to place our dice on the horizontal surface that we detect in augmented reality. So say if we're looking at a table or the floor, I want to be able to place my dice onto that horizontal surface and give the illusion that it is a part of the real world. So it's like when you play Pokemon Go and all the Pokemons appear on the ground. This is what we're going to be doing in this lesson. All right, so the first thing we need to do is I'm going to comment out the part where we created our dice. I'm going to come back to that later, but for now I just want to focus on detecting the horizontal plane. So if you go into your view will appear where you created your session configuration, I'm going to add another property to that configuration, which is, as we saw earlier on, the plane detection property. And I'm going to set that to equal dot horizontal. So as you can see, this is a enum. And if you don't remember what enums are, then have a look back at the intermediate Swift lessons where we went into that in more detail. But again, having the dot horizontal as an enum rather than having something like configuration dot horizontal plane detection equals true is another good indication code-wise that vertical is coming. All right, cool. So we've done that. We've said that let our configuration be a AR world tracking session configuration and enable horizontal plane detection on that configuration and then run it. So the next step is we need to use one of the delegate methods from the AR scene view delegate. And the one that we're going to be using is a method called did_add. So if you just start typing did_add with the AR scene view delegate adopted, then you will see this delegate method show up. And as it says, it tells the delegate, which is this current view controller, that a SceneKit node corresponding to a new AR anchor has been added to the scene. Okay, so a lot of new words here, but it basically means that it's detected a horizontal surface and it's given that detected surface a width and a height, which is an AR anchor, so that we'll be able to use it to place things or to visualize it. And I'm going to hit enter to insert that piece of code. And inside this did_add method is where we're going to set up our horizontal plane. So the most important thing that we get from this method is that when it detects a new horizontal plane, it's going to firstly call this method and trigger the code that's inside. But also we're going to receive this object called anchor. And the anchor is of data type AR anchor. So it's a real world position orientation that can be used for placing objects in an AR scene. So this you can think of as almost like a tile on the floor or on your horizontal plane. And you can use that tile to place objects. It has a dimension, it has a position, it has rotation, it has a whole bunch of coordinates, and we're going to use those real world coordinates of that plane in order to place our object onto it. So this anchor is what we're going to be working with. Now, AR anchor is a broad category of anchors. we want to specifically check to see if the anchor was of the type AR plane anchor, i.e. that anchor corresponds to a plane rather than some other sort of 3D object in the scene. So to do that, we can say if anchor is AR plane anchor. And this line of code basically checks to see if this new anchor that was added is of the type AR plane anchor, i.e. it is from our plane detection. Now, if that was true, then we're going to print plane detected. And if it's false or else, we're simply going to return, which means that we're just going to exit from this method call. So let's give it a go and see what happens when we try to detect some planes. Now, with ARKit, you notice that there's usually a bit of delay before it detects a plane. So we can enable one of the debug options, which will show us as it's trying to look for points in the view that are lining up to form a plane. So to do that, we're going to go right to the top of our view.did.load, and we're going to write self.sceneview.debug_options. And this again is an array, but we're only going to have one item in it, and we're going to use AR scene debug options dot show feature points. All right, so let's run the app again, and you can see the difference. All right, so that made it a little bit easier to see what was actually happening behind the scenes in order to enable plane detection. So it was looking for all of these feature points. And you'll notice that feature points don't get generated very easily when you have a sort of shiny metallic object. So if you go up to a mirror and you try to use the app to detect feature points, you won't actually get all that far. But if you have a soft fabric that has maybe some creases in it that casts a little bit of shadow and gives a little bit of texture to that plane, then your plane detection will work so much quicker and so much easier. But before the feature points actually appear on screen, your plane detection isn't taking place. So it's just a good way of being able to debug what's going on. All right, so now instead of printing that the plane is detected, I'm going to downcast our anchor into the type AR plane anchor. So I will say let plane anchor equal anchor as AR plane anchor. So our code basically checks to see if this anchor that was added or detected is of type AR plane anchor. And if it is, then we are going to change its type from AR anchor to AR plane anchor. Now, you'll notice that this is pretty wordy, and there's certainly ways of making this more succinct and much shorter on the number of lines of code. But because there's going to be quite a lot of things going on in this block of code, some of which is quite abstract and quite difficult to understand, I'm going to try and keep my code as expressive as possible for now, and then later on we can refactor it and make it shorter and simpler. So now we have this constant called plane anchor that is equal to the anchor that we got back from the delegate method, which detected a new area that corresponds to a horizontal plane, and we have changed its data type to AR plane anchor. All right, so the next thing that we need to do, we're going to convert the dimensions of our anchor into what's called a scene plane. So similar to how we created spheres and boxes using scene box or scene sphere, there's something called scene plane that allows us to create a plane in SceneKit. And we're going to call ours plane, and it's going to be created using scene plane. And scene plane only requires two things, a width and a height. So luckily the anchor that we've got, which is of type AR plane anchor, has a property called extent. And the extent comprises of a width and a height. So you can think of an anchor as simply just like a tile on the ground. And it has a width, it has a height, and we're going to use that tile that's been detected and convert it into something that we can use with SceneKit and that we can render onto our scene view. So the width is going to be plane anchor dot extent dot x, and the height is going to be plane anchor dot extent dot z. So a really important thing is that this is X and this is Z. A really common error is that people will write Y here, but if you actually read the documentation by option clicking on extent, you can see that this is the estimated width and length of the detected plane, and most importantly, although type of this property is vector float 3, i.e. a three-dimensional object, a plane anchor is always two-dimensional and is always position sized in only the X and Z directions. So make sure that you don't put Y in here because otherwise your code is not going to work going forth. Now the next thing you might notice is that Xcode is giving us this error here, and it's telling us that it can't convert the type float, which this extent.x is, into the expected type, which is cgfloat, which this function requires of its parameters. So we can go ahead and cast it into a cgfloat by just clicking fix. And we fixed the x, so now we need to fix the extent.z. So the next step is to create a plane node. So you remember when we created spheres, we first created the geometry using SCN sphere, and then we created a node to attach that geometry to. Let plane node equals SCN node. And then I want to set the plane node's position property. Plane node dot position equals SCN vector 3. So the x is going to be plane anchor dot center dot x, and y is going to be 0. The y position is going to be 0 because remember it's a flat horizontal plane. So there is no y element. We don't want it to be above the horizontal plane that was detected. And z is going to be plane anchor dot center dot z. Alright, so up till now, this is all pretty similar to what we did previously with the boxes and the spheres. Now the next thing that we have to understand is a bit of a tricky concept. Now the idea is that we're creating this thing called a scene plane, which is a rectangular, one-sided plane geometry of a specified width and height. So we specified its width and height using the anchor that was detected. And then we might think that we're done, but actually there's a slight problem because scene planes are created as a vertical plane. So if you have a look at this graphic here and the 3D key, the red is the X, the green is the Y, and the Z component is non-existent because this is a 2D object. Now, as you might remember, in ARKit, on our scene view, everything is 3D and also our plane is horizontal. So we need to convert this vertical plane that's got a component in the X and Y into a flat plane that's got a component in the X and the Z. So to do that, we're going to have to transform our plane node. And we're going to have to rotate it by 90 degrees in order to make it horizontal. So plane node dot transform, and we're going to specify the amount that we want to transform it using something called SCN matrix 4 make rotation. And this takes 4 parameters, first of which is the angle that you want to rotate it by, and then the next 3 parameters you specify along which axes you want to rotate your object. So the angle that we want to rotate our plane by is 90 degrees. We want to change it from vertical to horizontal. Now this is in radians, so just a bit of recap on high school maths. 1 pi radian is equivalent to 180 degrees. So in order to rotate this by 90 degrees, we need half pi radians. So I'm going to grab pi by writing float.pi. And this is something that's available in UIKit because if you're working with spheres, if you're working with angles, then you tend to need to use pi. Divided by 2. And that's specifying that we're rotating by 90 degrees. However, if you have a look at this function, you can see that the angle is the amount of rotation in radians, so we got all of that right, measured counterclockwise around the rotation axis. So we actually want it to be rotated clockwise, so because when it's positive, it's counterclockwise. So to cancel that, we just need to add a minus in front of it. So 2 minuses cancel out, and this is now rotating our vertical plane 90 degrees clockwise. And then we are going to specify the axes that we want to rotate around, which is of course the x-axis. And for the other two, we're going to leave it alone. So our rotation only has an x component. All right, so that is our plane node created and transformed. Now for our human eyes to be able to see it and evaluate whether if our plane was created in the correct place, we're going to need to give it a material. So in this lesson, there is a download for a grid.png file. And this is the asset that Apple provided in their example project for us to be able to visualize these planes. So we're going to use the same image. And the important thing about this image that you might notice is that it's a .png file type. And you may or may not know, but PNG file types have transparencies. So we'll be able to see through our grid and see the material underneath. And you're going to see really soon what that looks like. All right, so I'm going to drag my grid and once again into the art.sceneassets folder. And then I'm going to create something called grid material. And again, it's going to be created using scene material. So we've done this before, and we're going to set the grid materials diffuse.contents to a UI image, which is the one that we dragged in just now. So we're going to have to specify the folder. So art.scnassets/grid.png. Okay, cool. And we're going to assign this material to our plane geometry that we created earlier on. So plane.materials equals grid material. And finally, we're going to set the geometry of our plane node to our plane. All right, so the only last thing we need to do, as we did before with our spheres and our boxes, is to add our child node into the root node. So you can see that as a part of this delegate method, we also have this parameter called node, which gives us a blank node to work with. So you can either, as we did before, tap into the sceneview.scene.root node add child node, or we can just simply use this node that got created when the did_add delegate method got called. Node.add child node, plane node onto the scene. So let's give it a run and see what it looks like. All right, so there you have it. Just with a few lines of code and the assistance of ARKit, we've been able to implement an immensely complicated computational task, which is detecting a horizontal plane in the real world based on the image that's coming in through the camera. So you can pat yourself on the back, and we can thank ARKit for making our lives easier. So in the next lesson, we're going to be looking at how we can detect touch in the scene. Because ultimately we want to be able to touch a plane that we've detected, say a table or the floor, and be able to place our dice at the position that we touched in the 3D world and scaled so it looks like it's a realistic dice that's been placed in the 3D world. So we're going to do that in the next lesson, so I'll see you there.